Hi, everybody. I'm back. It's good to see a bunch of people here. Sorry I wasn't able to do those live classes during the last four, but I'm planning to do them. I'm planning to do them for the whole time through the course, unless some emergency comes up. So uh, I it looks like people did a really good job just looking at like the homework assignments and the Delta math, things like that. People are, in general, doing pretty well. From the text or from chatting, did you guys do? Did you do? Did you have live meeting yourself on the Google? Did people show up for that? Was there a collaborative? Okay, I see one person said yes. A few. Okay. Well, I think that's great. And from what I saw with the Delta math, it looked like people were understanding. Now, there's going to be some kind of a final project. My understanding is that everyone in this group is some kind of a teacher, either a math teacher or different kinds of teachers. Someone said that they're a special ed teacher. I think as a final project, you're going to create like a unit, like how would you teach some of this stuff to your students? What would, if there was something that you felt was appropriate for them, is there any way you can make math relevant, multicultural by, these different cultures, and make some kind of like a unit plan, like here's a topic I'd want to teach, and here are the lessons I would do. Maybe you'd write up like one lesson thoroughly. So I'm thinking that would be a good opportunity to, maybe you'll end up using that lesson, next year or whenever you're teaching. Anyway, today's one of the best days of like material. I really like the stuff that we're going to do today. So far, we have done two cultures. We did Babylonian math for the first three classes, maybe the first four. Then we did Egyptian math for the next three classes. And now we started in on Chinese math. Now, the Babylonian and the Egyptian was from way back in like 1600 BC. And this Chinese math is more recent than that. Kind of starts in like 500 BC. And in China, the sort of most famous mathematical book in China is called the Nine Chapters of the Mathematical Arts. Nine chapters. And this was a book that collected all of their knowledge about math. And I think they started writing it in somewhere around 500 BC. And then over about an 800-year period, they would keep on like adding to it and refining it and doing commentary on it. Well, those nine chapters, each one is like a top topic in math, like systems of equations is one of the books. But for us, a real interesting one is chapter 9. Chapter 9 is all about what we in the West call the Pythagorean theorem. Now, Pythagoras was in 500 BC, and the Chinese had what is the Pythagorean theorem. They didn't call, well, the Greeks didn't call it the Pythagorean theorem either. I mean, somehow we now call it the Pythagorean theorem because Pythagoras is thought to have done a really good proof of it. In China, they called it the kudzu theorem. And those two words, go and gu, actually are the descriptive words for the two legs of a right triangle. Go, gu. I'm not sure which one is which, whether there's the longer one or whether they're interchangeable. Anyway, in China, they call it the go-gu theorem. And in China, they still call it that. Some people do. Well, what is the Pythagorean theorem, or as known in China, the go-gu theorem? Why don't you type into the comments? What is it? That's right. It says how in a right triangle, the lengths of the three sides are related to each other. And what is that relationship? Like, if I said this was 5, or maybe make it simpler, if this is 6, and this is 8, and this is a right angle, how big would the hypotenuse of this right triangle have to be? Yes, it would have to be 10. And in general, what is the relationship if I call the small side A and the medium side B and the hypotenuse C? And that's right. Probably the most important and famous theorem in math. A squared plus B squared equals C squared. So yes, the Greeks knew it. In Babylonian math, they talk about the side and the diagonal of a rectangle. They seem to know it. And in China, they definitely knew it. And they have a really clever proof of it, because it's a thing that we learn. And like in pop culture, I would say the Pythagorean theorem is the most famous thing in math. Anyone have a thought about, is there anything that's more famous than Pythagorean theorem? I mean, besides like 1 + 1 = 2 or something like that, but like significant math thing is what could rival it as the most famous thing in math? Mm-hmm. Pascal's triangle, also something invented in China, but not named after the Chinese. Pascal's triangle is pretty famous. Mm-hmm. These are all good things about Fibonacci sequence and the equation of a line. When you think about like what you learn in high school and maybe 8th grade, these are all the things we learn. But Pythagorean theorem, whether it's the most famous thing or whether it's up there in the top 10, it is quite a famous thing. And it's a surprising thing also, because there doesn't seem to be any compelling reason like why should it be. I mean, we can test it, we can predict and say if this is 3 and this is 5, according to the Pythagorean theorem, this should be the square root of 9 plus 25 equals square root of 34, which is a little bit less than 6, 5 point something. What is the square root of 34? 5.8. We could check it and measure it, and it's something that seems to be true. But why? Is there some reason that it's true, or is it just something that is true? Well, most proofs of the Pythagorean theorem are based on a geometric picture. most proofs of the Pythagorean theorem are like this, starting with a picture of a right triangle. And we always think of a squared, b squared, and c squared as being like numbers, you know, a times a, b times b. But the reason why we call to the second power, we call that squared, is because geometrically a square has that area. 3 squared is 9, because if you made a square with sides of length 3, the area would be 9. So most proofs of the Pythagorean theorem start with, it's not just a triangle and somehow trying to prove that a squared plus b squared equals c squared, but it's usually a geometrical picture like this, and the idea that this yellow square and the red square, if I were to like a jigsaw puzzle, like obviously I can't just put the red and blue square and cover the green square with it, but maybe if I like cut things up, I can do that. And there are many visual proofs of Pythagorean theorem, and we're going to see some of them later on when we do some more of them when we do Greek math, which is the next culture. But drawing this picture doesn't prove at all that a squared plus b squared. It's just another thing, you know, it's just a starting point. How could I prove that those things are equal, that the blue and the red, that the yellow and the red squares together should equal the greens, the blue square, like if I cut them up like a jigsaw puzzle? It's not obvious, and we're going to look at a very specific example right here. Now this, and I have this on the handout, this is a picture from like an ancient Chinese text. What do you see in this picture? Because there's a lot of stuff going on. Anyone want to type in some comments? Well, what is this picture? Like, what is it composed of? What do you notice about this picture? You can type in some stuff into the comments. There are squares, there's a lot of squares, and there are right triangles. There are a bunch of small squares, a lot of them. Looks like there's 49 small squares. Yes, then there's these, it seems like important in this picture are these 4 right triangles. And they seem to surround that little tiny square in the middle. Yeah, there's also Chinese characters. I asked, I have a lot of students who speak Chinese as their first language, but they said that this text was like not like modern Chinese, that it was very like ancient, and it wasn't like something that you'd necessarily be able to read, even if you're a fluent speaker right now. What are these right triangles? What do you notice about them? Like, what are the dimensions of each of these right triangles? Yes, they are 3 by 4. So you look at that, and these are all 3, 4, 5 right triangles, or they should be. I mean, all we really know for sure is that we definitely have a 3 and a 4. Now, if we don't know the hypotenuse right now, we don't know that it's 5. Is there any way, based on this picture, that we can, without the Pythagorean theorem, let's say we don't know that 5 is the hypotenuse right now. Is there a way, by looking at this picture, that you could deduce that that hypotenuse would be 5 without using the Pythagorean theorem, but somehow something about this picture, think about that for a minute. What about this picture count the squares? Well, the squares in this, if we could show that this, if we could show that this big square is, you know, surrounded by this, if that has an area of 25, that would show that each side would be 5. Is there a way to verify that the area of that inner square must be 25 in this case? Now, someone said count the squares inside the triangles. Yeah, there's a bunch of like half squares and things in those triangles. So it would be hard to just like look at this inner triangle, this square, and locate, you know, are there actually 25? Like there are a bunch of full squares, then there are some like portions of squares. Maybe you could fit them together like a jigsaw piece. Ah, the 5 by 5 square. Do you mean like literally like draw it like here? Like that 5 by 5 square? So somebody said draw, because it's really hard to draw a 5 by 5 square at an angle. We can only draw them. I see cut the squares. Yeah, you might be able to actually take the pieces of the squares and they fit together. Well, the easiest way to show that the area of this square is 25 is by first calculating out the giant square. This large one is 7 by 7. So there are 49 squares in the picture. And these, there are 4 triangles. These 4. 1, 2, 3, 4. But I hope you can see that if I draw this in, that's a triangle that's equal to the other 2. So each 2 of those triangles makes a 3 by 4 rectangle. So if I take there's 4 triangles out here also, and those 4 triangles together make up 2 3 by 4 rectangles. So it's minus 12, which is 25. So I did it by removing this, 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 and this. Well, that shows that at least in this very special case, that the hypotenuse is 5. But we want more than that. Like that's good, 3, 4, 5 right triangle. A lot of cultures knew about the 3, 4, 5 right triangle. But there's more to this picture than that. So I want to go into it a little further and show you how this picture could prove not just that a right triangle with legs 3 and 4 have hypotenuse 5, but more general than that. By the way, I'm recording all this and I'll post this up also. One thing I could do is make this more general. AB. All the short sides are A. And all the medium sides are B. So the big square is A plus B squared. That's the thing that was 49 before. And when I subtract away the 4 rectangles, triangles, these 4. It would be 4 times 1/2 AB, which becomes A squared plus 2AB plus B squared minus 4 times half AB is 2AB. And the 2ABs cancel out. So if I call A plus B C, this is C squared is the same thing as, sorry, something went wrong here. A plus B is not the same thing as C. Sorry, got myself confused there. When you subtract away the four triangles, what you're left with is the thing in the middle. But that thing in the middle is A squared plus B squared. So that's all that's left when the two ABs cancel out. But of course, that is C squared because it's the square on the hypotenuse. So this picture can be like, prove the Pythagorean theorem more generally. It might look like I used the Pythagorean theorem to prove it, but I didn't. I did this identity from algebra, A plus B squared, and the area of a triangle is half AB. So there was no using Pythagorean theorem to prove the Pythagorean theorem in this proof. But we're not done with this proof yet because there's one more thing I want to say about it. Okay, so we did this one. But I have another. Let me glance at it for a second. Yes, let me come back here now. There's yet another way to look at this thing. Instead of subtracting the big from the big square, let's just look at the yellow, this medium-sized square, just as it is. That thing is C squared. And it's composed of 5 things. We're gonna do this one as an adding thing, not a subtracting. It's composed of 1, 2, 3, 4, plus the square in the middle. We haven't talked about that square in the middle yet. So it is 4 times 1/2 AB plus this little square in the middle. Now that square in the middle in this case is a 1x1 square. But in general, if this is A, if A is the short side and B is the medium side, what can you say about the dimensions of that little square, which happens to be 1x1 square this time? But it didn't have to be 1x1. Yes, it is B minus A because here's B, and then this little piece of it is A, and that little piece is B minus A. So that little square is B minus A squared. That one's tricky to see. I think I have, here's a bigger picture of it where it's not 3x4. 3x4 is a little deceiving because that tiny 1x1 thing just fits so perfectly. Here's the one we were just looking at. And it's kind of hard to see how fortunate that is, that it's 1x1 little square in the middle. So I want you to spend a second looking at this one. Here's a 5x12, here's like a bigger picture of this. And we can see a little better that square in the middle this time is not just a little square, a 1x1 square, but it would be a 7x7 square. The important thing about this, though, is that if you were to simplify this, 4 times 1/2 AB is 2AB, and B minus A squared is B squared minus 2AB plus A squared, and then the 2ABs cancel out, and again we get C squared equals A squared plus B squared. I suspect that this second interpretation, I'm not sure which way is better. I feel like this way is really good because it's using adding instead of subtracting, and the center square is like, it's kind of like bowls. Even in this, you see how it's like a little bit bold? So I feel like but maybe it's not bold, maybe that's just the boldness. Then again, it has some kind of name on it also, which could be relevant. Anyway, basically what I wanted to show you here is how this really ancient diagram reveals two different, well, three if you count like, oh, just 3 squared plus 4 squared equals 5 squared. But that picture is a really neat picture. It's really nice to look at like a ancient diagram and study it. For our purposes, if on a test I showed you this picture, I would want you to know that it's a way of geometrically proving the Pythagorean theorem. In the square root algorithm from the last class, there was a geometrical picture, and the Chinese use these geometrical pictures, sometimes called a dissection proof. If you take a geometrical shape and you like break it up into pieces and somehow do something with the pieces, they call it a dissection proof. And characteristic of Chinese math, you see a lot of these proofs. Okay, we talked about all that and all that and that. Okay, now here's another geometrical proof I want to show you. On the left, you see a medium-sized square and a small square. And this picture, by the way, is on the document. I try to make you like one document a day. It's got all like the diagrams you might need, and it's got the homework in it. Now on the right, we see a big mess, right? Well, look carefully at that big mess. One thing you might notice is that there's just really, I could turn the thing on the left into the thing on the right with a good choice. I'm going to get a different colored pen here. If I were to draw this line segment, and let's just call this A and this B. And that line segment I just drew is this one. So we have a nice right triangle. And you can see this often when we draw Pythagorean theorem proofs, it's so common to have a right triangle like this and make this A, B, and C and draw the squares sort of outside. But what if instead I still drew the B squared on the left? What if instead of drawing the A squared under, I draw it over? And instead of drawing the C squared to the right, I instead drew it to the left. Now look carefully at this picture on the right again. I hope now that you look at the picture on the right, what you see is actually 3 squares and 1 triangle. This here is A squared. This here is B squared. And I'll just outline this guy. I can make it thinner. And this here that's what this picture is. It's basically this picture with a square drawn from this corner to this one, and then just a square drawn. Now, it's not that obvious why this is definitely going to end up over here. Like on this, but it does. That's mainly because if this is B, and if this is C, and this is also C, this is obviously a right angle here. So this would have to be A. this angle has to be equal to this angle because this is a right angle and so is that. So whatever this is in the middle, this plus that has to be 90, and so is this plus that. It's not easy to see this. Now you see here a name. Now in Babylonian math and in Egyptian math, well, in Babylonian math, we don't have the name of, we don't have any names of mathematicians. In Egyptian math, like the Rhine papyrus, I think we know like the name of like the student who copied it, but that's not like the mathematician who like invented it. And we know a lot of famous mathematician names from Greece: Pythagoras, Euclid, Archimedes. But most people could not name for you not one famous historical mathematical figure from Babylonian times, Egyptian times, or Chinese times, from ancient times in China. Well, if you're going to take history of math, you should know that this name, Liu Hui, is the most famous mathematical name, kind of like whatever Archimedes is to Greece, and Archimedes is kind of like a household name. Liu Hui is the major historical mathematical figure in China. And he's around 200 AD. He wrote a commentary on the 9 chapters of the mathematical arts, where he like enhanced it and did amazing work. So I do want you to know this name because that is not a household name in the West. Okay, I want to show you a very slick proof. Here's that picture, but I made the medium square blue and the small square red. Also, I want you to notice that I drew in an extra line. I drew in an extra line right over here. I also want you to notice that the red and blue, let's number these pieces. Let's call this blue triangle 1, and this smaller blue triangle 2, and this like quadrilateral thing 3, and this sort of trapezoid thing 4, and this little triangle 5. Does anyone see the trick to showing that the a squared and b squared as a jigsaw puzzle is equal to the c squared? Is there a way to rearrange the pieces? Why don't I call the missing spots? I don't want to call it A, B, and C. I'll just call it D, E, and F. Anyone want to say something about this picture? How to show that the 5 pieces, 1, 2, 3, 4, 5, can be reassembled to make the slanted square, the C square? Exactly right. If you take the piece from number 1 and put it into E, and you take the piece from 2 and put it onto F, and the piece from 3 and put it onto D, pieces 3 and 4 are on the overlap, and they're part of both things. I think I have, here you go, is that it? Yeah. Look at that. I really like that. It's like, to me, it's like you take this overlap piece, which is this weird thing, and that thing. So this like odd shaped thing that I've just outlined, and if you add those three pieces one way, it becomes c squared. But if you add them another way, it turns into a squared plus b squared. So this is commonly thought as Leo Wei's proof. They speculate that this is his proof because they don't have a diagram, but they have a lengthy description in words of what he does. And he actually talks about the red and the blue. So we usually color it that way also. But that's a really slick proof of what they called the kudzu theorem. So what we've seen today are a couple of geometric proofs. The rest of today's class is about word problems that involve right triangles. Those of you who are math teachers, what are the most famous word problems that involve right triangles? What household objects that we use are involved in right triangle word problems? Anyone want to type in some right triangle word problems? Yes, a ladder, right? Pretty much you so often see nowadays, we so often see this where it's a ladder. They say, oh, well, I have a 13-foot ladder and I want to reach to a spot that's 12 feet high. How far is this from here? So ladders. Lamppost. How does the lamppost work? Is there, where's the hypotenuse in the lamppost? Or the flag? Oh, is the flagpole have a shadow? Yes. So yes, you have a thing sometimes with a shadow, and they want to know how long is the tip of the flagpole to the tip of the shadow. There's one other that's pretty famous, right triangle with a household object. Picture's not that great. This is not a good picture at all, but maybe this will help. It's like Pictionary. What is that supposed to be? Well, it's not a good picture. That's someone flying a kite. So sometimes they want to know, like, if this is 100 foot of string, how high is the kite? If the kite is, this much. So kites and ladders and distance from the wall and shadows. That's what we often see today with these Pythagorean theorem word problems. Well, in the 9 chapters of the mathematical arts, they end the chapter. I'm sorry, they don't end the chapter. The chapter is 24 word problems that involve right triangles that they have to use a squared plus b squared equals c squared in. But none of them are ladders and kites. And actually, these are questions that I've never seen, and I taught math for a long time. And some of these questions I had never really pondered before. It's not that they're so hard, just that for some reason, we're so stuck on the ladder and the kites and things like that. So here's an interesting question. The broken bamboo. The bamboo is 10 chi high, which is a unit of measurement, and it's broken so that its tip touches the ground 3 chi away. What is the height of the break? So here, so the tree was the tree was like this, that's before, and then it got broken here, so that now it's like that, with the top of the tree is on the ground. And they say that this is 3, and they want to know what this is. How tall is the break, meaning this portion from here to here? Well, that's an interesting question, because normally we're so used to knowing 2 out of the 3 sides, and here I only know 1 out of the 3 sides. Let's call that the unknown side x. Does anyone know how we can continue with this question to figure out what x is? Well, often these answers do end up being perfect squares, but not this time. Like, this is not going to be like a 3, 4, 5. Yes, 10 minus x is the length of the fallen part of the tree. So this is a really interesting question because something funny happens in it. It's not usual. It's not like the question we're used to seeing where 2 sides are known and then you have to eventually like take the square root of something. When you run this through the Kudzu theorem, something really interesting happens that in all my years of teaching math until studying this 9 chapters of mathematical arts, I had never seen happen before. And what is that? What happens now that rarely happens in modern Pythagorean theorem word problems? Why don't you go ahead and, yes, these squares are eliminated. You can subtract x squared from both sides. So there is no needing to take the square root. And I'm honest with you, I've taught 6th grade math, I've taught high school math, I've taught all levels of math and gone through many books that have Pythagorean theorem word problems in them. Just, I never encountered one, this question, where the x squares cancel out. So we're left with 9 equals 100 minus 20x, or 20x equals 91, or x equals 4 and 11 over 21. I don't know what levels of math you teach, those of you who are math teachers, but have you ever seen a question like this that does not require square roots and things being perfect squares? So that's called the bamboo question, and that is question number 13 on in the 9 chapters of the mathematical arts. Oh, the reason we subtracted the 10 minus x is because before the tree was 10. And if the break afterwards is going to be x, whatever this leftover piece is 10 minus x. Like, imagine the break was 4 from the bottom. This would be 6, because they have to add up to 10. So x together with 10 minus x adds up to 10. So whatever the x is, the other piece is 10 minus x, because the whole thing was 10. Yeah, that could be. Is that more clear? Now, I posted on the homework 14, no, not 14, because questions 1, 2, and 3 were just like, if the 2 sides are 3 and 4, what's the hypotenuse? So I left those off. But I have questions 4 through 14, which is 11 questions. And this is one of them. question number 6. We're going to do 3 of them, then we're going to be done for today. I'm going to have you work on the other 8 for homework. Okay, here's question 6. Question 6 says, this is another great question. You have a reed at the center of a pond, 1 zang square. In their units of measurement, chi is kind of like a foot, and a zang is like 10 feet. It's 10 chi. Now, here's what they're saying. We have this pond, which is 10 across. And we don't know how deep this pond is. But there's like, they call it, there's a reed that's growing from the bottom, and it's going up, and then it pops up above by 1. Let me just move this 10 over because it's getting in the way. So this is, I'll go like this, 5, 5, and that's 1. So this is the reed. It's growing. It's a long reed. It goes from the bottom, however deep that is, to the top, and then peaks out above by 1. Now, they say this isn't enough information to figure out how deep the water is. So they give us another information. It says, when it is drawn to the bank, it is just within reach. That means if I take the top of this and I kind of pull it in this direction, this happens. This reed is, whatever this is, that's what this is also. So at the edge of the bank, it just touches the surface of the water. And they want to know how long is the reed. So they want to know how long is the reed, which is from here to here. Anyone have a thought about what I can call this red side of this right triangle? Because here's the right triangle. It's formed by, it's right here. And I want to say something about the red side? Because we know this little 1 here. Yes, it is x minus 1, and that is because from here to here is x, because that's the same reed as this. This and this are the same. So if this little 1 is taken off, that red piece is x minus 1. Okay, I would like you to now that the diagram is created, go ahead and figure out what x is. And you could, Chad, if you want to unmute yourself and talk about it, I'm going to mute myself for a minute or two while you work on this. Good, and I see a lot of x equals 13s. The work would be 5 squared plus x minus 1 squared is equal to x squared. 5 squared plus x squared minus 2x plus 1 equals x squared. Again, the x squareds cancel out, and 2x is equal to 26, or x equals 13. So far in this course, the main mathematical things you needed to know, and this was for the Babylonian math, and also in this, was the whole a plus b squared equals a squared plus 2ab plus b squared, or a minus b squared. In this case, you would need that a squared minus 2ab plus b squared. So those are like that's mainly the mathematical prerequisites for the course. And that's also an interesting question, which I never encountered in all my study of ladders and kites and things like that. Now, I'm only going to do one other question today, but there are 8 other ones for homework, and they can be pretty difficult to interpret. So I drew some diagrams for them, but this third one is like one of the hardest ones to visualize. This was question 5. So what we've seen, that was question 6. Look at this question. There's a tree that's 20 chi high and 3 chi in circumference. A vine winds around it 7 times from its root to its tip. How long is the vine? Now, this is quite a question because there's no obvious. Chapter 9 is all about right triangles. Oh, there's someone been waiting to come in. There's no obvious right triangle in this picture. And they talk about the circumference of the tree, which is kind of strange. It makes us feel like, do I have to calculate out the diameter of the tree and use pi? Do they know pi? Well, let's see if this animated thing works on my thing. Let's see, ready? Check this out. Again, the tree's 20 chi high and 3 chi in circumference, and you see that vine winding around it. It just doesn't seem that possible. Now, if it wasn't winding around it, like imagine this was the situation and it was just on the bottom, 1, 2, 3, 4, 5, 6, 7. Like in that case, how long would the vine be? If it wasn't winding around, like if it wasn't winding around, like snaking its way to the top, like that thing, what would it be if it was? Yeah, it would just be 7 times 20. No, sorry, not 7 times 20, because 20 is the height of the tree, but the circumference is 3. So it would be 21 in that case. But that's not what's happening. It's not just winding around the bottom 7 times. It's winding like this. It's like hard to, I really didn't draw it that well. It's kind of making it like a barbershop pole. Does that mean it should be more or less than 20? Yeah, it's going to be more than 20, but not that much more than 20. You know, like not. It's going to be more than 20 for sure, but maybe not so much more than 20, but definitely more than 20. I should have said more than 21. I mean, it's going to be more than 21, but how much more than 21? Well, I hope this works because this animated GIF. Let's see. Check it out. Does it work? Yes. Here I'm unraveling it. I'm going to do something with a piece of paper that I'm going to put my camera on for. Maybe that helps also. I'm going to turn my camera on for a second to see if I can show you this. Okay, now can I see myself? Hold on. Okay, so here's a right triangle. And if I roll it up like this, what you can see, if you look closely, this outline, this here, you could do this yourself. Just roll it up. And the vine kind of becomes, see this edge of the paper kind of winds around, just like a vine would. It makes like that spiral. But when I unravel it, it becomes a right triangle. That's all you'll see of me today. And that's why the answer to this question is actually 29, because the height, the right triangle that's created, this is 20, and 21, wait a second. Now I got myself confused. Hold on a second. Yes, 21's down here. I got myself a little bit confused. And we have this right triangle. We have the 20. The 21 has to do with the 7 times 3, but I just have to think about that for a second. When I unroll that, that piece of paper, they're like, because it winds around 7 times, I had to sort of unroll it, sort of seven rolls around, and that's why the 21. So the 21 came as the 7 times 3. The 20 is the height of the tree, and this here is the unrolled vine. And then you just, this one does become where you have to take the square root, and it ends up being the 20, 21, 29 Pythagorean triple. Anyway, that question is very hard to visualize. I'll encourage you to make a triangle out of paper and roll it around to sort of convince yourself about the bottom. I'm going to put myself back on so I could look at. So when it rolls around 7 times, when it unrolls 1, 2, 3, 4, 5, 6, 7, the bottom turns into 3 times 7 because 3 was the circumference of the tree, and it was 7 rolls. This becomes the vine, and this is the top. Anyway, that is a very hard question, and it's one that now you'll be familiar with. So if on a test I ever give this question, you'll know exactly, that the 20 is this, that you can make your right triangle, and that this, even if you're not fully convinced that this does actually become a triangle and expect it to become something different, I promise you that it does become a triangle, but it's hard to visualize. So we've done 3 of the 11 questions. Now I have here diagrams, which I put into the document also, because question 4, oh, here's question 5 that we just did. You see over here, that's the one with the, it's funny, I don't put the 21. Oh yeah, because I didn't want to give too much of a hint. So question 4 and 5, we did 6 already. I guess 7 or number 8 is maybe more self-explanatory, but here's diagrams for 9, 10, 11, 12, and for 14, because they're hard to know. Like number 9, that question is particularly, so your homework is to do the rest of the questions, 8, 9, 11, 12, 7. Basically, you're doing questions 4 through 14. Hold on, my iPad freezes for a sec. So you're doing questions 4 to 14, but we already did 13, 6, and 5. Those were the vine question and the broken tree and the reed. So that leaves 8 questions. Now I have diagrams for some of them. And number 14 is particularly hard. It's okay if you don't get that one, but it is worth spending some time trying to figure it out. And I'll show you how that one works. The unrolled vine is the 29 itself. The 21 is not like, the 21 is, if there was a vine on the bottom that was all at the bottom, that's what would unroll to 21. But the vine itself is the 29. Oh, I see, I have answers. Where are the questions? Let me bring the actual questions up because I have those also, so I can just show you them. They are in the, they're in the document, but here, let's see, lots of windows here. Okay, history of math for teachers. And here is document. So you see we have the different pictures that we did, and then I've got the questions. Some diagrams might help you out. And here they are. Now these have the answers also. Now number 4 says there's a log. Kun is 1/10 of a chi. Do I have a picture for number 4? I do. I have a picture for number 4. It's hard. It's about a log that's turned into a plank. There's so many ways to turn a log into a plank. They mean like this. This is the cross section of the log, and they cut it out so it's a nice, so it's like a rectangular prism. 5 we just did. 6 we did with the reed. 7 is one of my favorite questions. I definitely want you to do 7. Like that's one of the most important ones. If you do just one question, number 7 is a really important one. So did I make a diagram for it? I did not make a diagram for it. So that's a really interesting one. And number 8, that's also an interesting one. I really like questions 7 and 8. Number 9 is a weird question. There's a log buried in a wall. So I gave you the diagram for that because this here is the wall and the log is like pushed into the wall like sideways. So it makes a shelf. Like, I don't know how you would actually do that, but that's what the picture looks like. This here is the wall. This is the log. It's like in this little piece of the wall is embedded in it. And I have pictures for the other ones. 10 is double doors that you're opening up. Those end up making like here are the doors, these slanted ones. They went like, sorry, this trapezoid thing is like the wall and the door opens like that. Anyway, these questions are not easy, but I would like you to spend time messing around. You could talk to people about it. I might just, I'll transfer control to someone else because there's still, we've only been here for an hour. But if you can answer as many of these 8 questions as possible, I'm going to admit to you that number 13 we did already. Number 14 is really, really hard. So let's think of 13 as 14 as like a challenge question that you don't have to do. But the other 7 questions, I want you to try. Let me bring the iPad back up. Okay, so there's questions 4 through 4, let's say 4 to 13. But if you get 14, that's a real challenge. So 4 to 13, except we've already done these 3. So that leaves 7 questions with 14 as a challenge. Not just a challenge, but it's extremely hard, number 14. So why don't you guys work on it together? It's 7 questions all together. And we have diagrams for a lot of them you can discuss. Plus you have the answers, because on the sheet it also says what the answer is, so you can try to see if you can achieve that answer. Anyone want to volunteer to become the host when I leave? Who's good? Somebody want to figure they'll stick around for like an hour and get the homework done? No, nobody feels like they want to work together with neighbors while they're here anyway. Okay, great. So Amber, I'm going to transfer the control to you. And if you have to leave in 15 minutes, for whatever reason, you could transfer it to somebody else. Try to work on the 7 questions, the 7 other questions. I put them in an order where like maybe from easy to hard, but I'm going to leave the meeting now. So I'll see everybody. Oh, hold on one second. Anyone have any questions before I go and leave you to working on trying to work these questions? Okay, well, I'm going to transfer control to Amber. Let's see how this works. First of all, I'll stop the recording and I'll post this later.